Good day, I'm Norman Walberger. In our last few videos we've been talking about higher kinds of data structures where we combine lists, ordered sets, multi-sets, and sets inside each other. We're going to give a very important application of that kind of idea today, turning to things called arrays and matrices. These are very important kind of two-dimensional tables, usually occupied with mathematical objects, often numbers, which arise in many different places in mathematics. They really have a very central role in linear algebra, group theory, graph theory, algebra, applied mathematics, and many other things. Okay, so sometimes we write them with square brackets, sometimes there's kind of round brackets like this. And there's different terminology, so the word array and the word matrix are often used interchangeably. So a natural question is there a distinction between arrays and matrices? And for us, there will be. Okay, this is not necessary, but we are going to think about arrays as looking like this, and matrices as looking like this. And there will be a difference. Today we're going to be talking about arrays. So a natural question is, how do we define these things precisely without requiring a prior theory of two-dimensional space? Obviously there's a two-dimensional aspect. There's a length and a width. We're extending a certain amount in a certain direction, a certain amount in a perpendicular direction. How do we say that without going through all of Euclidean geometry or something similar? Of course, we could just write down a picture like that and say that's a matrix or that's an array, but there's something a little bit unsatisfactory about that, right? Here's a foundational series of lectures. We want to pin things down precisely what they are, not rest too much on our physical intuition. In fact, we'd like to not rest on our physical intuition at all. We'd like to say things so precisely that even a computer, which is completely devoid, say, of any physical or visual intuition or understanding, can understand what we're talking about. In this video and the next, we are going to be giving precise definitions of array and matrix. And we're going to treat these as separate but closely related concepts. And our point of view has been motivated by our discussion of these data structures that we've been talking a lot about, what we call LOMs, which stands for lists, ordered sets, multi-sets, and sets. These are the four basic types of ways of organizing things that we like to use. Okay, so let's start off with the idea of an array. So let's first of all fix a natural number n, much as we've been doing for all of the discussion of these four basic types of data structures. And now we're going to define a j by k array from n. We're going to define what that means. So what it is a list of lists of a particular type, list of list nk j. So I remind you that list nk refers to a fundamental kind of list with k elements, each of which is a natural number from 1 up to n. Those are the ingredients, and there are k of them strung together to form a list. Now this bigger list contains as objects lists of this kind, and there are j of them. So it's a list of lists. So let's be specific. For n equals 5, and say j equals 2, and k equals 3. Here is an example of a list which has 2 entries, and this one here is a 3 list, and this one is another 3 list. So this is a 2 list, the j would be 2 in this case, a 2 list of 3 lists. This is what we would call a 2 by 3 array from 5, because all of the entries are between 1 and 5. And instead of writing the list of lists like this, we're going to write it in a sort of array notation like this. Okay, introducing the two-dimensional aspect, where we have the first list along the first row. Here, as a list, the thing had to be separated by commas and contained in a square bracket. Here we just have the entries separated by spaces, just in their right positions. And then the second list, 553, is spread out there in the second row. So that's what we do. We take all the lists in our list of lists and create a row for each one of them. So there's going to be as many rows as there are entries to this big list. So this is an example of an array. It's actually a 2 by 3 array from 5. So if you've done some computer science, this will be very familiar kind of concept, because this is the way a lot of programs think about what arrays or matrices are as well. And we'll talk a little bit about that at the end. So here's another example. This array, B, is a 4 by 2 array from 3. 3 because all the entries are between 1 and 3. So officially, as a list of lists, we would write it down in list notation with the square brackets, and then we would list the first row as a list, a 2 list, and then the second row as another 2 list, the third row as another 2 list, the fourth row as another 2 list. So we have a list of lists. So it actually contains 4 2 lists from 3. So the 4 2 lists from 3 give us a 4 by 2 array from 3. So we're going to agree that these two ways of writing B are equivalent. That they're just two different ways of visualizing or expressing the same object. This is just another way of writing this thing here, which is a little bit more spread out, a little bit easier for us to appreciate because it has a two-dimensional aspect. We can sort of see more clearly what's going on. There are not a lot of commas and brackets that might confuse us. But on the other hand, your computer might be a lot happier with this kind of object, which you can just read along and you can check that all the brackets are in the right spots, there's commas in all the right spots, and it knows exactly what it's talking about. So this B is a list whose elements are 2 lists from 3. And there's 4 of them. But we also now going to introduce an alternate type name, because we don't always want to be talking about this as the type of object. We're going to say that B is of type array 3, 4 by 2. So in keeping with our general convention that the first spot refers to where the actual elements are coming from. In this case, we're talking about elements from 3, in other words, numbers 1, 2, or 3. And then the second entry tells us something about how big it is, or its dimensions. In this case, it's 4 by 2. 4 by 2. So this is a very efficient way of describing this type, which is probably easier for us to understand than lists of lists, but really they're equivalent. All right, so this is a new type of object, and this B is an example of that type. Let's introduce just a little bit of notation so that we can talk a little bit more efficiently about the various aspects of these arrays. So suppose that A is an array from N of dimensions j by k, or a j by k array from N. Then it has j rows. So as a list of lists, it's a list of j lists, where each of these objects is itself a k list from N. And we can talk about these lists, which are the components of this thing, as the rows of the array. So that fits in keeping with our two-dimensional picture, where the actual rows are what we would usually consider to be the rows of this array. If we look at any one row or list, say the ith one, AI, then we've said that that's going to be a k list from N. So it actually has k entries. And sort of in a consistent kind of way, we could refer to those k entries by a numbering system where the first one is A sub I1, and then the next one is A sub I2, all the way up to a sub ik. So that these two indices which are appearing here are telling us, first of all, which list in here we're talking about. And then the second entry is telling us which entry of that list we're talking about. The first entry, the second entry, the kth entry. So here a sub il has the property that I runs from 1 to j, telling us basically which list we're in. And L runs from 1 to k, telling us which entry in that particular list we're talking about. And we will use the word entry, so these things here, which are actually numbers, are going to be the entries of A. So then we can rather efficiently write the array in this kind of notation with the square brackets and A sub il, just reminding ourselves that this is an array whose typical entry is the form AIL. And if we know it's a j by k array, then we know that I is running from 1 to j and L is running from 1 to k. So it does take a little bit of getting used to this kind of notation, having these two dimensions. The I going from 1 to j, that would correspond to going up and down in the rows of the array. The L going from 1 to k would represent going across the columns in the array. So this one here, the I, is indexing the rows of the array, and the L, the second entry, is indexing the columns of the array. So it's an excellent idea for students to get on top of these notational conventions for arrays, because they figure in linear algebra very prominently and in other areas as well, calculus too. So a lot of mathematics is made a little bit simpler if we are comfortable moving around in an array and being able to find where we are very precisely. It's like just coordinates, but it's a little bit different because instead of having x and y coordinates, which with the x going first to the right and the y going second up, in this case we're kind of doing the opposite. We're starting here and the first coordinate is kind of going down, and then the second coordinate is going across. So there's a little bit of potential to get things mixed up with the usual Cartesian coordinate system of labeling things in the xy plane. So just to reinforce what we've said, let's have a look at this array again. So here's our array B. It's an array from 3. It's got dimensions 4 by 2. So it's a 4 by 2 array from 3. 4 rows, 2 columns. Okay, so the actual lists which form B are 1, 3. That's the first row, really the first list. And then the next one, B2, is 2, 2. The next one, B3, would be 2, 2. The next one, B4, would be 3, 1. And if we look at any one particular row or list, say B1, there it is there, then the first entry is a 1, while the second entry is 3. If we look in the second row, B21, that's the first entry in the second row, that's a 2, and the second entry in the second row is also 2. Similarly, in the third row, the first entry in the third row is 2, the second entry in the third row is also 2. When we get down to the fourth row, the first entry in the fourth row is 3, the second entry in the fourth row is 1. Okay, so this general framework now is quite pleasant. It actually generalizes in nice ways. So one way that we can generalize things is by thinking about this N from which all our elements are chosen. We may not always want to specify the range of elements that we're talking about. It's very nice when we do that. It clarifies very concretely where the entries are coming from, and if someone is reading this, then they have a kind of a safe feeling because they know that the entries are not going to get too big. It's kind of a guarantee that we're only going to go up to 3 and no more. But nevertheless, in some situations, you want to maybe be more flexible and maybe not say which natural number the entries are going to be restricted to. You might want to keep that open. Okay, so it's no big deal in doing that. We just modify the idea a little bit, still employ the same kind of notation, same idea. We're talking about an array, and in the first entry we're going to specify the range of entries or elements. So if we put here nat for natural numbers instead of n, like n equals 3 or n equals 5, then we're allowing the possibility that the entries can be any objects of this type. Here this is a 3 by 2, it's still specifying this is a 3 by 2 array. The dimensions are the same, but now there's no particular bound on these entries. They could be rather big, which might be good, might also be a nuisance. I mean, you know, if someone comes up with an entry there and that entry is, takes 3,000 kilometers to write down in 12-point type, you might not be that happy about it. All right, so that's an advantage in having a specific bound that we know that this thing is reasonable. In principle, when we talk about nat there, well, these things could be really huge. But of course, when we give examples, like here, typically we choose very small numbers so that we're all comfortable and we confident that we know what we're talking about. Once we allow the possibility of having a type like natural numbers there, well, then it's not a big step to enlarge that and think, well, we could put integers there. Okay, so we could think about arrays whose elements are integers, still of a particular size. So if there were integers here, then this could be a minus 114, this could be a 0, this could be a minus 71. Or we could go one step further, we could talk about rational numbers. So we could put rat there, that would tell us that the entries have to be rational numbers, so then there could be a 17 over 4 and a 3 over 2 and a minus 21 over 97 and so on. But again, then there's no bound, and so in principle you could have rational numbers with huge numerators and huge denominators, and effectively the thing could actually blow out on you. Okay, that's the price you pay by not bounding the range in which these elements are coming from. So it's a trade-off. All right, so that's a very flexible kind of arrangement that has a lot of different applications, but we can also extend it or generalize it in another very interesting and important way. In fact, the notion of an array generalizes to higher dimensions. So let's have a look at that. So here's a more complicated kind of list. It's a list because there's square brackets and there's a comma. And this object is all one object, and that's also one object. If we look at this thing here, well, we see that that's also a list whose entries are two lists. So this is a list of lists. This is also a list of lists. So C is a list of lists of lists. An array was a list of lists. Now we're talking about a list of lists of lists. That's what it is. And if we look more carefully at sort of the sizes, well, we see that the maximum number is a 7, so all of the elements are from 7. So we could say this is a list whose size is, first of all, 2. There are 2 objects. And each of these objects is itself a list of lists. This is a list of 3 lists whose objects are 2 lists from 7. And this is also a 3 list consisting of 2 lists from 7. It's actually a 2 list of 3 lists of 2 lists from 7. Rather a mouthful. So that gets quite complicated to say it that way, even though it is rather precise. So we can introduce this shorthand exactly in keeping with what we've been doing in the 2-dimensional case, and say that C is actually an array from 7 of dimension 2 by 3 by 2. 2 times 3 times 2. So it's a 2 list of 3 lists of 2 lists from 7, or just a 2 by 3 by 2 array from 7. And so just as we've visualized a 3 by 4 array, say, in terms of a rectangular array of numbers on a paper, so we can visualize this kind of higher dimensional array as entries arranged in a three-dimensional box, sort of the three-dimensional analog of a rectangle. So here's an example of a 4 by 3 by 2 array from 5. It's named C. So it's a 4 by 3 by 2 array. That means that it's got 4 entries. And each of those entries is a list with 3 entries. And each of those 3 entries is a list with 2 entries. So when we read 4 by 3 by 2, we're kind of reading from the outside. So the big picture is that there's 4 entries, and then we look at any one of the ingredients, it's got 3 entries, and then we look at any one of those ingredients and we have 2 entries. All right, so we could think about this in a number of ways. First of all, we would recognize that this first thing is exactly the kind of two-dimensional array that we've been talking about. This is a list of lists. In other words, this is a two-dimensional array. It's actually a 3 by 2 array. And there it is right there. It's the array 1, 2, 7, 4, 3, 5. That's a more efficient way, for us at least, to write down what's going on with this first entry here. This second entry, this list here, for us is written 5, 4, 5, 4, 3, 1. A computer might be much happier with this kind of description. The next entry, 6, 1, 1, 6, 2, 2. And the final fourth entry, 3, 5, 6, 4, 7, 1. So here's another way of thinking about this array as 4 3 by 2 arrays. That's a 3 by 2 array, that's a 3 by 2 array. There's another one, there's 4 of them all together. And now if we want to visualize that all at once, well, we might think about a three-dimensional box. And the way to think about that, at least one way, is to think about each one of these arrays sort of being stacked on top of each other in a third dimension, which is in a different direction from the dimensions that we're actually using in the array there. So here's a little box that perhaps helps you visualize that. So this first 3 by 2 array is sitting there in that sort of first part of this box. The box is divided into 4 sections. And so you can imagine maybe having solid numbers that occupy that first quarter of the box. And then that second quarter of the box, that layer there, although we can't see it, you can imagine this array sort of put in there. There's another 6 numbers behind these numbers. And then behind those, there's this array. And then in the final sort of segment of this box, there is the fourth 3 by 2 array. So we have these 4 3 by 2 arrays all together filling out a 4 by 3 by 2 box. So that's a way of visualizing this three-dimensional array. I mentioned that this approach to arrays is very traditional and is really following standard practice in computer science. So most programming languages that deal with mathematical structures, at some point they want to talk about arrays or matrices or something equivalent. And so they have various conventions to sort of define these things and allow people to enter matrices or arrays. So for example, Maple, which is a powerful mathematical computing environment coming from Canada actually. We use that at UNSW in our first year courses. So that has this kind of convention for creating a matrix, and it's, you'll see, very familiar. So matrix, and then some brackets, and then in here we have a list, and then there's a comma, and then here there's a list, and there's another list. That's exactly the same kind of thing that we're doing, and the output is exactly the same as what we're doing. So, except that we're not using the word matrix in this bracket, but I mean the idea of a list of lists and the way we write down the list is exactly what we're doing. Python also uses essentially this form. Mathematica, which is Stephen Wolfram's brainchild and a very powerful environment for doing mathematical computing. Uses something similar, but the convention is slightly different. So there's braces here. The lists are represented by braces. There are still commas, and otherwise it's very much the same. And the output is perhaps an array in round brackets. MATLAB, very commonly used in engineering applications. So for that you can input a matrix rather efficiently, like this, 1, 2, 3, and then a semicolon, 4, 5, 6. That will input that matrix there. So the approach to arrays that we've been laying out here is very tried and true and will be familiar to many of you. But for those of you to whom it's not familiar, it's really important to get on top of it. There is something to be said a little bit, though, about this approach. So in all of these approaches, what we're doing here is we're emphasizing the rows a little bit above the columns. We're introducing a little bit of asymmetry because we're agreeing that we're going to read off and in fact specify these objects row by row. So if you'd rather think about things in terms of columns by columns, well, then that doesn't quite mesh with this, or you'd have to take a transpose to go from one to the other. So it turns out that there's another way that's quite interesting of specifying matrices. And what we're going to do is we're going to separate what we've done today, which is going to be the theory of arrays, from what we're going to do next video, which is going to be matrices. And what we're going to exploit is the fact that, in fact, we have these other kinds of data structures around, not just lists. We also have ordered sets and multi-sets. We've already seen that there's some kind of interesting connection between multi-sets and lists, and we're going to exploit that to show you a rather novel way of thinking about matrices. And this novel way of thinking about matrices is going to, curiously, open some doors for us that are not so easy to find otherwise. All right, so in our next video, a slightly novel way of thinking about matrices, again firmly rooted in this data structure orientation that we are developing here. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.